press enter. Beneath the plastic, a mechanical switch compresses and a spark of electricity fires, starting the journey of a digital message. That signal enters a web of millions of independent networks. This decentralized architecture was designed to maintain communications even if large sections of the grid were destroyed. In 1969, the challenge was making these incompatible networks talk to each other. The Department of Defense funded ARPANET, an experimental system that connected 4 research nodes across the United States. The TCP IP model grew out of that experiment, while other organizations proposed a highly detailed 7-layer framework called OSI. TCP IP became the global standard because it was practical, protocol-driven, and already deployed. The system works like a restaurant kitchen. Each layer performs one specific job and hands it off. The waiter doesn't need to know how the chef prepared the meal, and the chef doesn't need to know which table ordered it. Everything starts at layer 1, the application layer. This is the interface where your software interacts with the network, translating human commands into formatted digital data. When you type a web address, the browser generates an HTTP GET request. This document contains a header identifying what resource it wants and a body for the data itself. Supporting protocols gather the necessary metadata. DHCP automatically acquires a local IP address for your device, while DNS translates the human-readable URL into the specific numerical IP address the network requires. The request is prepped and formatted. It now begins its descent through the network stack to be prepared for the physical journey. A request arrives at layer 2, the transport layer. Its primary role is end-to-end communication, ensuring the data moves reliably from your application to the application on the other side. It chooses between 2 protocols. UDP is designed for speed, dropping data if it arrives late, ideal for live video. TCP is methodical, checking for errors and ensuring that every byte arrives in the correct order. To ensure the web page loads perfectly, our request uses TCP. It establishes a connection through a 3-way handshake. The client sends SYN, server replies SYN ACK, and client confirms with an ACK. TCP breaks the request into segments, wrapping them in a header with sequence numbers to reorder data, and port numbers identifying the application. This process adds data overhead to the original message, but it provides a reliability guarantee. A web page cannot afford a single missing or out-of-order byte without breaking the entire application. The segment moves down to layer 3, the internet layer. Here, the focus shifts from end-to-end reliability to global addressing and routing. The entire TCP segment is placed inside an IP header, officially becoming an IP packet. This header acts as the shipping label, stamped with source and destination IP addresses. While 32-bit IPv4 is common, the network is transitioning to the 128-bit IPv6 format, providing enough unique addresses to cover the massive growth of internet-connected devices. Global routing protocols read these addresses to navigate the packet through the network. To prevent lost data from circulating forever, each packet includes a time-to-live value that counts down at every router it passes. Layer 3 acts as the system's mapmaker. If a specific cable is cut, the routing logic calculates a new path, ensuring the packet reaches its destination across the global network. The packet reaches layer 4, the network access layer. This is the hardware interface, where software instructions prepare to become physical reality. The packet is strapped into an Ethernet frame. It is stamped with MAC addresses, unique physical identifiers burned into the hardware of your device, and sealed with a checksum to detect transmission errors. At this point, the digital frame is shattered into raw binary bits. The formatted data is ready to leave the computer, and so those bits become physical energy. They travel as voltage fluctuations and copper wires, radio waves in the air, and pulses of light inside the glass cores of fiber optic cables. At this boundary, our message ceases to be abstract code and becomes physical energy, traveling across the planet's hardware. The physical bits arrive at the destination server's network interface card. The server begins decapsulation. It strips the Ethernet frame, verifies the IP destination, and checks the TCP sequence numbers. The final header is removed, delivering the original HTTP GET request to the web server application, exactly as sent. The server generates an HTTP 200 OK response containing the actual web page data and sends it back down through the same 4 layers of encapsulation. This entire global round trip typically completes in under 50 milliseconds. The speed of the process makes the massive complexity of the network invisible to the user. The architecture we just followed is currently handling billions of concurrent processes across the entire planet right now. The model scales because the layers are independent. A smartphone and a mainframe can exchange data using the same protocol stack, while the routing architecture handles hardware failures by recalculating paths in real time. This flexibility involves trade-offs. The model has reached absolute IPv4 address exhaustion, lacks built-in security at the protocol level, and provides no guaranteed quality of service. While security and encryption have been retrofitted on top, the foundation remains the blueprint drafted by Vint Cerf and his team in the 1970s. TCP/IP is a physical choreography running beneath our feet. Every keystroke triggers a global sequence of wrapping and unwrapping intent, connecting the planet in the time it takes to blink.